There's another one on combinatorial metamaterials, which will be probably one of the topics in Yair Shokev's talk next week. So instead of these topics, I will go back to something that's been going on for a little bit longer than this past year, and talk about some ideas that hopefully you will find interesting. It's about knots. Well, we are masters of the knots, so we'd better look at them, see what's going on. And there is one interesting pattern that I would like to point out. So this topic lies at the intersection of low-dimensional topology, more specifically the study of knots and their quantum invariants, and on the one hand, and on the other hand, in algebraic combinatorics, where we are going to look at some lattice polytopes, and which will typically come from graphs, and then there will be some kind of Erhard theory, which I don't have much time to work on. Here's this one slide only, just to give you an idea, just in case anybody out there remember this maybe from high school. You may have seen this. It's called Pick's formula. It has to do with the case when the dimension is n equals 2, where you can consider some sort of a convex lattice polytope just in the plane. And then there is this classical formula for its area, which expresses it in terms of discrete data, such as the number of lattice points in the interior, also the lattice points along the boundary that you have to take 1/2 times, and then you subtract 1. That's supposed to compute the area of this continuous object in the middle. All right, so you can check that actually this works out in this example. So this was just an excuse to say the definition that a lattice polytope is going to be a convex and compact set, so bounded and closed in n-dimensional space, so that its vertices lie in the n-dimensional lattice, just like the vertices of this object did. All right, so how that's going to come up, you will see that soon enough, because I mean it's not immediately obvious why such a thing would have anything to do with knots, but let's move in that direction. So the connection happens through the Humphrey polynomial. I will just say Humphrey polynomial, even though there should be also the letters P and T at the end. This is one of those objects that Luke Kaufman talked about last week, so maybe you remember. In case you don't, here's a very quick review of what's happening. So this is a 2-variable, actually Laurent polynomial. Laurent just means that exponents can be negative. Otherwise, it's just a nice finite expression in those 2 variables. You associate such a thing to an oriented link, L, so the input needs to have an orientation on it. And the way this is determined is that, well, of course, it has to be an invariant. Isotopy invariance is a key property. It's normalized at the unknot being evaluated to 1, fairly natural. And then the key and most important thing is the scale relation that this thing satisfies. There will be a very concrete, hopefully, computation of the Humphrey polynomial later, so you will see how this works. But, well, maybe you do know how it works. So what you have to concentrate on are these 3 little kind of indices. Should keep them visible. So locally in a knot diagram, you may find such a thing. And then you can just sort of erase that and locally replace it with this other picture, which respects the orientation, but the crossing is the opposite. Or you can smooth the crossing that also respects the orientation. And you don't touch the diagram anywhere else. All right, so that way you generate 3 diagrams. Each one of them has its associated 2-variable polynomial. And those 3 objects are related by this simple linear relation, where the coefficients, of course, well, they include the actual variables v and z in the Humphrey polynomial. All right, so this is something that you can actually easily compute. There will be a concrete example a little bit later. On the other hand, it's fairly difficult to understand what the heck this is doing. Well, but you know, it might be very relevant to perhaps even to what you are doing. in applications. Oh, this thing here is, I've written it here because in Luke Hoffman's talks last week, the same polynomial appeared with the variable a, which is just the inverse of my variable v, just in case. Don't get confused. So you may be wondering what the Humphrey polynomials of your favorite knots are. So here are some concrete examples. So everybody's first non-trivial knot, the trefoil, has this Humphrey polynomial. Oh, actually, I should start from here. This 3 terms only. Let me rearrange them. Same 3 terms, but I have written them now in some sort of more regular way, so that the z exponent increases upward and the v exponent increases to the right. And if you do that, then of course it's sufficient just to keep track of the coefficients that you can plot. I'm gonna keep doing this, so that's why I'm saying this in so much detail. So you make this plot of the coefficients where the horizontal axis corresponds to the exponent of v, the vertical axis corresponds to the exponent of, sorry, that's actually z. Oh, that's why one has to do talks on an iPad, so that when I notice that there is a typo, I can immediately fix it. That was z, sorry. Okay, so the figure 8 has a similarly simple Humphrey polynomial that becomes this if I plot it on a plane with the exact same convention about the axis. Just for examples. So let me also remind you, this might be interesting to some, that the Humphrey polynomial is a pretty good chirality test. So if you are wondering if the knot that you're looking at is chiral, that is to say, is it equivalent to its mirror image or not, then evaluating the Humphrey polynomial is a good idea, because when you mirror a knot, you go to M of L instead of L, the mirror, then the Humphrey polynomial changes to this. It's the old Humphrey polynomial, except that instead of v, you have minus v inverse. A fairly simple transformation. However, such a transformation can change a polynomial, and when it does, when this happens, then you know L must be chiral. So it's kind of practical for that. But it's not a fail-proof test. In fact, just to have another example, here is this guy that kind of tricks this test. The Humphrey polynomial in this case looks like this. It is actually invariant. It has this relation with equality. I mean, it's symmetric, as you can see. Substituting v inverse to v just mirrors the coefficient to the other side, and this array of coefficients is actually symmetric under that. So, all right. From the polynomial, it looks like as if this knot was achiral, but in fact, it is chiral. That is revealed by some other technology called the signature.
So,
yes.
So in other words, polynomials are not good enough test, right?
It's not a perfect test, correct. It's a pretty good test. So for example, it does reveal that the trefoil knot is chiral. So this polynomial, if I do the substitution, becomes this. It reflects to the other side of the axis, certainly shows that the trefoil knot is not equivalent to its mirror image. There's a right-handed trefoil, which is on this picture, and there is a left-handed trefoil, and they are not isotopic. And that's definitely revealed by the Humphrey polynomial, but doesn't work in every single case.
And then you would apply for mirror symmetric or amphichiral knots that can have some configurations that in each instance can have chirality, although you can morph it to the other chiral state, right? Yeah. Well, in those cases, the polynomial is always the same, yes, right?
Such as for the figure 8. So Luke Hoffman showed it on his piece of rope, right? How you transform into the mirror image, and well, indeed, this polynomial is symmetric, so no contradiction at least.
So in other words, the non-chiral are detected bulletproof, but
yes,
maybe
exactly. It's a one-way implication, not a two-way. Okay, but let's just kind of look at this Humphrey polynomial kind of in a very simple thing. I mean, what if you come across a notion like that? I mean, how would you try to understand it? Maybe you would just look at some examples. see what's going on, try to get a feel. And maybe you also want to simplify the question. In my case, what I'm going to do is to start from the top. Start from the top of this. So far in the examples we have seen, oops, that's not going to go well for me. In the examples we have seen, the top was a single -1 here. Let's make it kind of bolder. Single -1 here, single -1 here, single 1 here, pretty simple. And in fact, you will notice if you do this, that the top of the Humphrey polynomial is often very short. Let me show you some bigger examples in case you care. These are some pretty randomly selected 16 crossing alternating knots. I just looked it up on the web. There are tabulations of knots, of course. Took some, see what, these are fairly typical in that the top is very short, and then it kind of widens on both sides, right? And then there's a big array of coefficients. So, you know, just for us to get a feel of what this polynomial is doing. Okay, so the top, all right. So this next thing here is really only for the knot theorists out there, in case you have heard these words. There's a reason for the top being so short, and that is that it only depends on the Seifert graph. In fact, only depends on the reduced Seifert graph of the knot diagram. And Seifert graphs, in fact, tend to have a bunch of multiple edges. And you can kind of forget them when you only look at the top. So the Seifert graph reduces to typically something very small, and therefore you get a very, very short thing on the top. Okay, so how do you beat that? I'd like to, you know, come up with something more exciting than just 1, 1. Okay, so one way to manufacture examples that are more interesting is this. So this construction starts from a graph G. So here's an example right away. The graph is this red structure in the middle. This one is the graph. I want it to be bipartite. I wrote this in this funny way to explain the color convention here, which is that every blue vertex can only be connected to green ones. So blue and blue are never connected, and green are never connected. That's the rule for a bipartite graph. So that's what you do. You pick one and you draw it on the plane. Not all graphs can be drawn on the plane, but you pick one that you can draw on the plane. All right, so there's the knot. The knot is, well, first there is a surface, FG, G is the graph. This surface, FG, is constructed from disks. So what is that? So just imagine that you have flattened your graph into the plane. So now you can put a little disk around every single vertex. Okay, so you can do that. And you can also connect these disks by twisted bands. So that's like this stuff on my diagram, this one. Those are the connecting bands for the surfaces. You want it to twist because you want a knot, right? If I didn't twist that band, then the boundary of this construction would just be a bunch of trivial circles, not very interesting. But because of the twisting, there is going to be a lot of coiling. It's going to get tangled up. It's going to be something interesting. And indeed, so I should also say, though, that the actual link or knot is the boundary of this surface. So that thick black curve, in this case, it's actually a 2-component link, because as you can see, there's this trivial component on the outside, and there's a trefoil component in the middle. That's what happens in this particular case. So when you take the Humphrey polynomial of this, this happens. Sort of an unusual shape. Maybe if you compare it to my previous examples, it's fairly different in terms of the shape. So it's manufactured that way, and I kind of know why this is happening. One little thing that will come up later. So all these crossings that I made are actually so-called positive crossings. There was a discussion of that too last week, right? What to call positive and what to call negative. Anyway, this is what I decided to call positive, and that's the standard convention. That's the way this is built. The twisting of the bands, the twisted bands, are actually all negatively twisted. and that makes all the crossings, in fact, positive. Oh, well, for that to make sense. Oh, by the way, if I'm speaking too fast, or if there are any questions, please do stop me. For example, right now, yes, David.
So I can see that this graph is sort of dual to these disks, but the unshaded regions are also disk shaped. So
Yes.
like, what exactly is the duality relation?
Well, so there's a big difference, though. Indeed, you're right in pointing out that the unshaded regions are also disks. Surely they are. So the big difference, though, is that is exactly the orientation which I forgot to emphasize. So everything is constructed in the orientable sense. So these disks that I started with actually get orientations. In fact, in such a way that around green vertices, they are oriented clockwise. Around blue vertices, they are oriented counterclockwise. Sorry, that was not successful. This is what I mean to say. Opposite. And that's exactly why I want this to be a bipartite graph, so that this makes sense. There are vertices that are clockwise and others that are counterclockwise. This is very important in this structure. That's responsible for the fact that all vertices, all crossings kind of look like this. So the arrows always point kind of perpendicular to the original graph edge, etc. And I just choose the twisting of the bands in such a way that every crossing is positively oriented, is positive. So the orientation rule is just like this. I can do it around every disk, but as you can see, that actually orients the whole thing consistently, etc., etc. I did say, though, right, that for evaluating a Humphrey polynomial, you need an oriented link. So that's the orientation, and that's actually important. More questions, perhaps? Yes. Okay. So more examples. So Luke Kaufman also mentioned this basic Celtic knot pattern, and it's actually one of these constructions. So I couldn't resist showing it here. So that's this kind of the graph here is this finite planar lattice, right? Something that does come up in applications. For this particular number of edges this way and this way, the Humphrey polynomial looks like this. Again, you see that the top of it is fairly interesting. That's the way this is manufactured. Another simple model of a knot is the so-called pretzel knot. Pretzel because it has these pretzel strands. If you pick the parities well, in this case, I actually pick them all odd and odd and odd, actually 5 and 3 and 7. These are the coefficients here. Anyway, the Humphrey polynomial of that is this thing here. It looks even more peculiar, right? So anyway, this class of knots, these are certainly very special types of knots, but they serve as very nice building blocks if you want to look at the Humphrey polynomial.
So you say the polynomial looks peculiar, but can you somehow relate the structure to symmetry or something like this? Some other aspects of it.
Well, symmetry, I'm not sure what symmetry it is, but that's what I'm driving at. It's going to be related to something hopefully surprising. It's coming up in a couple minutes. Right. Okay, so so basically we are going back to the beginning here. How do you compute a Humphrey polynomial? Well, I said that there are some super simple rules that you have to follow when you do that. Here they were. Most important being this Kane relation. Well, because in my construction, the knots I will be looking at, every crossing looks like this. Well, it makes sense then to rearrange the Kane relation, this one, so that you just kind of solve for the Humphrey polynomial of that positive crossing. I mean, the diagram that contains the positive crossing. That's expressed with the Humphrey polynomial of the same diagram with the negative crossing like this, and the same, I'm sorry. Yeah, the same diagram with the crossing smooth with this other coefficient. So simple algebra, right? The coefficients become v squared and vz. All right, and then the way you actually compute a Humphrey polynomial is that you apply this rule repeatedly to the diagram, and hopefully, this is going to be a computation that happens in finite time, and of course it does. So here's what it looks like in a super concrete case. So the goal of this talk essentially is to go through this one computation. This is kind of a tutorial, all right? Very concrete diagram of a concrete three-component link. I just want you to follow along a little bit of how the Humphrey polynomial of this is computed. And then I will explain some patterns that emerge in here. Okay, so here's the start point. Notice that this is one of those things I'm talking about. There's a graph underneath. It looks like this in this case. This is my graph. It's certainly bipartite. That's what I constructed my example from. Okay, so how do you untangle this thing? Maybe you choose a base point, and maybe you start walking along the knot in the given direction. And maybe you come to a first crossing, and the curve dips under here, right? It reached this crossing, it's trying to go under, and maybe you don't like that. Maybe that's the rule. You don't like that. So then you change. So you apply the scaling relation at this site. Okay, so that means replacing that site with the opposite crossing, or replacing it with the smooth version of the same crossing. And you do not touch the diagram anywhere else. Okay, so that's the point. Nowhere, the rest of it out here never changes. I mean, at this stage, it doesn't change. Okay, let me actually first go in this direction. So, well, you got rid of that crossing, right? Observation. Oops. Oh, what was that? Okay, very well. Got it. Then what? You're sharing screen. That's very good. Hopefully we come back now. Cool. Everything okay? Maybe it's a good time for questions. All right. So this side of the computation, we have made a little bit of progress here, right? Okay, but maybe we start from the same base point, we go along again, and here still this curve is trying to dip under that other strand, and maybe we still don't like that. Okay, so we apply the scale relation a second time to this side. So that means either smoothing that side or changing the crossing at that side and not touching the diagram anywhere else. That's what we do. So this is interesting here. So just by these two steps, what happens here? Well, if you look at this diagram, you notice that it is actually not knotted at all. Oops, I don't know. That didn't have did it. It totally uncoils, right? Can everybody see that? So that's progress because we know that it's the unknot. The Humphrey polynomial of the unknot is supposed to be 1. So at this stage, we don't have to do anything else with this guy, right? We are done here. Why did it become the unknot though? That's important. That's because the remaining graph here is just a tree. A tree in graph theory, we call a graph a tree if it is connected and without cycles. And indeed, just by removing these two edges from the original graph, the remainder has no cycles anymore, but it is still connected. And then when the graph is like that, the corresponding diagram is always unknotted. No nothing anymore. Okay, but there are still, these byproducts that we have to deal with. The scaling relation is a free-term relation. So for example, this still remains. So here, maybe I apply my same way of thinking, start from here. Okay, it's going over, good, going over, good. Here it's going under, but this is just a trivial kink. Let's just ignore that. Let's go on. And then here we come here, where it's still trying to go under. So that's where I will apply the scaling relation again. So instead of this positive crossing, I will have, something like this, or something like this. Okay, By the way, so what's happening here? I haven't emphasized it yet, but I should, that whenever I do this move, this simplification move, the graph changes. How does it change? Well, either it loses an edge. Let me go back to the first step. From here, we went to here. Here, the graph simply lost an edge. This edge is not there anymore. But otherwise, you have this smaller graph, and to this smaller graph, you are applying the same procedure to create the knot diagram. So you don't lose this nice connection between graphs and knots during the computation. Here, on the other hand, well, here the crossing changed, so the edge is still there, but now it means a negative crossing. The crossing changed from positive to negative. I can keep track of that too by decorating the edge. In this case, I just drawn it dotted, right? That's to remind us that the corresponding crossing changed. It's not of this type, the positive type, but the negative type now. So I will later on too, I will call the original edges positive and the modified edges negative.
Question.
Yes.
So why not just use oriented edges in the graph?
You could do that too, totally equivalent, but well, yeah. It's an equivalent formulation. I find this more satisfactory for what's going on, but you're totally right.
And you said that a tree always corresponds to a knot. I assume the converse is not true.
Absolutely not. Yes, there, as Luca Opan showed us last week, you can draw super complicated diagrams of the unknot. Don't look like a coiled tree at all, but yet they are unknotted. Yes, indeed, the converse is not true. So, okay, where was I? So, okay, so from here, we went here. We got our first tree. There was a side product, though, which we operated on. And from out of that, we got our second tree. Okay, that's also a tree. And indeed, the corresponding diagram, as you can see, is unknotted. But there is a side product of that step too, which is this. Luckily, though, here I can stop my computation. Why? Well, if you look at this diagram, you see it's an on-link now. By doing these crossing changes, we pushed this component completely under the other component. So you can just slide out from underneath, and the other component, the one on top, is also unknotted. So this is the so-called two-component on-link. The Humphrey polynomial of that is well known. So instead of computing on, I'll just put the answer here. Remember what this means, right? This is the v exponent thing, the z exponent thing. So this term here is actually v inverse z inverse. This term here is minus vz inverse. Whatever, that happens to be the Humphrey polynomial of the two-component on-link. All right, we are actually close to finishing this. How am I doing with time? Okay, not too bad. Well, except that we haven't done this part yet, right? So there was this side product on this side of the computation tree. Well, so here the rule maybe chooses this crossing to operate on, which you smooth or you change. Okay, then in this diagram, maybe you choose this side that you smooth or you change. All right, so this is in fact your third tree. That's going to be significant. And the other one is again an on-link. Shall I zoom in? Maybe I should here. See, this is yet another on-link with the same Humphrey polynomial. All right, there is still this guy too. This is actually not an on-link. You can see that there is an on-knot on the top of it. That's nice. You can just slide it away, get it out of the way. But the other two components still form a hop link. Oh, well, because there is no more room on this slide. I haven't computed continued the computation, but I did write the answer here that this happens to be the Humphrey polynomial of this object. Okay, so what are you supposed to see here? Well, so how does the Humphrey polynomial of this guy actually get computed? Well, you go to the ends of this computation tree, however many you had so far. you take the Humphrey polynomials at these ends of the computation tree, and then you multiply these polynomials with the product of the labels of the edges that connect the particular end back to the root. That's how you put it together. Well, so if you do it in this case, you notice that, so for example, this tree, I said that the Humphrey polynomial weight is equal to 1. So then when you go back to the root, it picks up 2 copies of VZ. So that places the contribution here. So maybe just for once, I should remind you that this is a V exponent 2. Oh, why is it so thick? V exponent 2, and this is Z exponent 2. So the contribution of this tree is this one term, this single term in the Humphrey polynomial. The contribution of this next tree is, well, it's also 1, because it's the unknot, times, well, same to VZs, but for this guy, there is also a V squared. Right? So where does this land? It lands 2 units to the right of the previous, right here. It's one of these 2. The other one is coming from the third tree, indeed, because you see it's the same labels, 2 VZs and the V squared. Same set of labels, their product is the same. So the 1, which is the Humphrey polynomial of this, ends up in this position. So what happens is that it's exactly the trees that are responsible for the top, and the other stuff that I haven't even completely computed does not contribute to the top. You can check if you care. So this is at Z level -1. This keeps it at the same Z level, This brings it up by 1 level to level 0. So these 2 terms actually go here to the middle, not to the top. Okay, they do not bother the top. That's my point here. The trees make up the top. The other stuff does not touch the top. That's a two-way implication, in fact. Right, so let me see what I had in my notes that I skipped so far. So there is a systematic way to carry out this computation, not just in this example, but in any example, so that the contributions to the top only come from, well, certain spanning trees. Well, in fact, they are signed spanning trees because they pick up decoration along the way. For example, this tree, if I zoom in, has its edge here decorated. It's a negative edge. Why? Simply because we came to that tree like so, and this step was a crossing change step. So yeah, and the tree remembers that by having this decorated edge, the negative edge. The same way for the third tree, it has 1 decorated edge corresponding to this very first step here where a crossing change happened. Okay, so that way you get signed trees. Their contributions they each contribute a monomial with coefficient 1, and those contributions make up the top. Okay, we touched on this. The unknot is 1. Yes, very well. So one observation in general is that the number of VZ steps for a tree required to reach a tree, to get to a tree, is always the same. Well, why? Because you have to kill all the cycles in the graph. Originally, you had this graph, it has some number of cycles. You have to puncture them one by one until there are no more cycles, until you get to a tree. The number of times you have to do that is exactly the so-called first Betti number of the graph. And it's always the same for every tree. That's why maybe I should show it here. In my example, when I actually look at the top, VZ always came up twice, because the original graph that I had, this one here, has Betti number 2, has like 2 independent cycles on the 2 sides. Betti number 2 has to be punctured twice to get a tree, and that way this term is the same for every tree. The number of V squared events, that varies from tree to tree. in this example, it was 0 times for the first tree and 1 time for the other 2 trees. So summing of the contributions is 1 plus 2v squared. Okay, so very good. I actually went through this computation maybe even more quickly than I intended. So I will stop here in case there are questions. Yes.
So the reason why only trees contribute to the top row is that anything else would have a positive Betty number, and so it would get fewer C's.
It's worse than that. In fact, the dilemma that this other junk, this other stuff that appears in the computation, that none of this contributes to the top, that's the hardest part of the paper, of the particular paper where we published this result. The proof of that lemma is not a nice proof. That takes a long time. So there is no easy way to state the reason for that, but it's true. We tracked very rigorously that's just never happens. All the top is always coming from just the trees. Okay, maybe I should also say that these are not all the trees of this graph, just some of the trees. Some of the trees that the computation happened to produce. Somehow it landed on these 3. Okay. Any more questions? So here, well, so this was basically a tutorial on how you compute the Humphrey polynomial, right? A nice concrete example.
But you know, this is just one of the ways, right?
Sure.
So
yes, I of course hit something here. I said there was a systematic way. I decided not to explain in detail how exactly I want to carry it out, but it's not ad hoc. There is a completely systematic way that we can construct this type of computation tree. And if you do it that way, then the following things can be deduced.
because you know, there are these short mathematical codes that would compute all polynomials.
Yeah.
Once you know.
Absolutely. So the goal of this talk is not so that we get very good at computing complete polynomials. Of course, computers will always be able to do that much faster. The goal of this talk is to notice a certain pattern that I'm trying to point out. Okay. So, and it has to do with this polytope. So that somehow miraculously appears here. So I'll just have to kind of foist it on you. The root polytope. It starts with the same graph G, which is a bipartite graph. Every vertex of that can be treated as a vector. I guess people do that. Why not? And then a classical idea is that every edge of the graph should be treated as the difference of those 2 vectors at the endpoints. This is a completely classical idea in mathematics. And then, well, although you should complain that I said difference and I didn't say which I subtract from which other, but remember that the graph is bipartite, so you can choose at the beginning that, for example, you would always subtract blue from green, and that way this is well defined. So blue from green. So let me first say what the root polytope actually is. You take your graph, you take these sort of vectors, you take these differences, and then you take a convex hull. That's the smallest convex set containing all these vectors, some sort of a span, very natural concept. And you do this for all edges of G. So here is what it looks like in my very example, right? We worked on this graph on the previous slide. This is our graph. It's got 5 vertices. So we make all of them vectors, just abstractly. Think of them as the standard basis vectors in a 5-dimensional space. And then to each edge of the graph, associate the corresponding difference of the 2 vectors. That's going to be 6 vectors. And it turns out that they are arranged in exactly this way. So here they are, 1, 2, 3, 4, 5, 6. Turns out that even though the space is 5-dimensional, the dimension of this convex hull is just 3. Wonderful, we can see it. It's right in front of us.
So you said the vertices are associated to vectors, but You just choose any arbitrary vectors in any dimension.
Well, I mean, if in mathematics speak, I construct a vector space in which the vertices of the graph are the basis vectors. If you want, you can just whatever number the vertices of your graph and associate to the first vertex the vector 1, 0, 0, 0, 0, then to the second vertex the vector 0, 1, 0, 0, 0, etc. So yeah, just do some sort of totally natural correspondence like that. So a very lucky coincidence is that the dimension reduces from 5 to 3. It's actually always the number of vertices minus 2, as long as this graph is connected. And in this case, is this very simple polytope, right? It's a prism. Everybody can see the structure of this. Triangle at the base, and then there's certain height, and another triangle at the top. That's it. And then also very luckily for the presentation, the correspondence is totally natural. The upper left edge is the upper left vector, right? It's between W0 and U1, and I have U1 minus W0 right here. Okay, the top middle edge is this top middle vertex. Top right is this vertex, etc. Very easy to follow, I hope. Because what I'm going to do next is I will try to bring the two things together, right? So we did two things with this graph so far. We turned it into a knot, and we computed the Humphrey polynomial of that knot. And we also associated this polytope. So the key idea will be, what happens if I look at that computation, look at the 3 trees that came out of that computation, and I put these trees into this polytope. Okay, this is just one of those crazy things that mathematicians do, right? Well, but let's do it. Let's do it. So here's this is the first tree. It consists of these 3 edges and this edge, right? So it's going to be all 3 vertices on top and the right vertex on the bottom. Okay, these 4, only these 4, and those span this tetrahedron. This one here. All right. Second tree. So there, this is not a vertex anymore because this edge is gone. Instead of that, I have this new edge. So that's the bottom middle vertex, this one here. And it's again a tetrahedron, but now it's like this one. And the third tree also becomes a tetrahedron. Same way. Yes?
What are you doing with the negative edges here?
Well, so far nothing, but I'm going to say something very important about them. Indeed, just because they are negative, so far I've ignored that. I associated the exact same vector to them as to the positive ones. The significance of the negativity will be different. I'll come to it in a minute. Well, actually right now. So what do we notice? Each tree becomes a simplex, all right? Simplex is just another name for triangle or tetrahedron, the n-dimensional generalization of that. In our example, each tree became a tetrahedron, all right? Key thing is that the simplices do not overlap. So in some sense, this is where the magic of this is. See, if you look at these 3 guys that were generated, they very nicely fit together right next to each other. They don't bother each other, right? This second one in the middle fits very neatly right under the first one, right next to it, very snugly. And then the last one fits exactly into this hole that was still left after the second simplex. So these 3 simplices fill up the entire polytope perfectly, without overlap. Okay, that's basically the key observation. The magic is in that observation. There is a little bit more detail. These simplices actually come up in a particular order, right? I numbered them, 1, 2, 3. Well, if I go way back here, that was some sort of a clockwise order in which they came out of the computation. And if you think about the simplices in that order, then it's not random. It's not random at all. There's a first one, and then the second one fits right next to that, and then the third one fits right next to the second one. In general, what we are able to say is that, first of all, it's all these simplices form a triangulation of the root polytope. That's going to be a general fact. And this order of the simplices is a so-called Schelling order, in case you heard that. If not, forget it. What it means is that all these simplices attach to the previous ones very nicely along a certain number of faces. Okay, so that's the kind of thing that mathematicians love, when everything is just so regular and no weird exceptions to anything. Right, negative edges. Here it is, the attaching faces. So that's key for the actual result that comes out of this. So here, first tree, nothing special. Second tree had this negative edge. The negative edge was actually the new edge, right? The edge that was not present in the first tree. So that's why it's highlighted here with this big dot. Right? This was the bottom middle, right? The bottom middle was the new edge. The significance of this position of the negative edge is that it's exactly the face that is opposite to that, which is where the attachment happens to the previous stuff. This is the previous stuff. This new simplex attaches to that along the face, which is opposite to the point that came from the negative edge. That's the pattern. Same here, right? The negative edge is this, is exactly the new edge again that was not in the construction before. So it's pretty automatic in this case that the face which is opposite to that is the face along which this simplex attaches to the union of the previous two. That's what's happening. This is also a wonderful pattern, nice enough so that, forget this, so that you come to a theorem. So this is, I got almost exactly 10 minutes left. So this is the time in the talk where I kind of have to stop being so detailed. So please, for the last 10 minutes, bear with me while I'm stating 3 theorems about this situation. Here, so far I have tried to explain every term concretely. In the last 10 minutes, that's not going to be completely possible. So first theorem, joint with Hitoshi Murakami, is that for any graph you start this process with, the top of the Humphrey polynomial is expressed in this way. So this is the generalization of my formula. Which one? This one. In general, the top of the Humphrey polynomial looks like this. There's a VZ to the something term. I explained that one. And then there's a polynomial that I mysteriously call here H star of QG. So that's the gadget that comes out of this thing called Ehrhart theory, which I didn't have time to explain. I would love to talk to you about it in case anybody cares. The point about it is that this H star does not depend on the triangulation at all. The triangulation was just an artifact. Doesn't matter. H star, the polynomial, belongs to the polytope itself. Yeah, and of course, if you make you look at the same knot and maybe you start your process at a different point, you're gonna end up with different trees. Those will also triangulate the same polytope, but in a different way. In any case, what the computation ends up with does not depend on the triangulation, obviously. All I can say about this H star guy is that when you plug in 1 for the variable, that's just the sum of the coefficients, right? Algebra. So the sum of the coefficients in this H star is the volume of the polytope. So H star polynomial is kind of like a fancy volume. That's how I often think about it. All right, so that was the first theorem. Very nice, maybe, but there's at least one problem with it. This root polytope that appears in it, QG, is a combinatorial object. It doesn't quite naturally appear in the topology. It's really, yeah, it's kind of an artifact. But there's theorem 2. which says that there is an alternate way to compute this this polynomial H star. Well, I mean, the first way being that you triangulate and you keep track of certain data as you through the triangulation, and you, I don't know, and end up computing H star. The alternative way is going to break the symmetry, cardinal sin in mathematics, and instead of G, you view G as a hypergraph. So by breaking the symmetry, I mean that the blue vertices will be still called vertices. However, the green ones will be called hyperedges for the purposes of this one slide, and maybe the next one. And then, well, after that, you look at this structure called the hypergraph. It's really just the same as a graph, actually, except that edges can connect more than two vertices. That's it. That's a hypergraph. Anyway, in that, you can define so-called hypertrees. Maybe I will say a word about what it means. And then on the hypertrees, you define a certain activity statistic. Okay, getting hairy here. And then the next theorem, joined with Alex Postnikov, states that the distribution of this activity statistic that I dubbed the interior polynomial is exactly that H star thing. All right, why would you go through the pain of this? Well, before I give you the final answer to that, let me just quickly show a few, just say one word about these hypertrees. I really would like to do this in case anybody sees a pattern like this. Hypertrees are actually really cool. Well, so if you have seen a pattern like this in your work, please let me know. Okay, what are they? In our case, these are just possible degree vectors taken at one of the colors only of the spanning trees of this graph G. All right, let's actually do it. Here's the example graph. We singled out green to be the hyperedges, so we are going to keep track of vertices, degrees there. So what can a spanning tree of this guy do? Well, it can have many vertices up here, many edges up here, and then a single edge down here. In that case, the degree vector is going to be 3 here, 1 here. Or we can kind of start trading, right? Maybe we get rid of this one and bring in this instead. Well, then the degree vector is 2 and 2. Or we can go 1 and 3, and that's where it stops. These are the only 3 options in this case. They, in fact, form a linear alignment. There's 3 points linearly aligned. Well, if you somehow fancy the other color, because you can do that too, you can break the symmetry the other way. Look at degrees at these 3. Well, they can be, well, I mean, to make a tree, you have to connect top and bottom somewhere. So where you connect here or here or here, the degree is going to be 2. And elsewhere, it's going to have to be 1. Again, only 3 options for the degree vector. These 3 vectors form a regular triangle. So these 2 shapes, very simple in this case, generalize to something called a polymetroid, also known as a generalized permutohedron, or an M-convex set. It's much studied in mathematics, and it should show up in physics as well. So if you see it, let me know. Finally, so why do I care for this alternate way of computing H star? Why is the triangulation method not good enough for me? Well, that's because I have a theorem. This one is joined with Andreas Juhász and Jake Rasmussen, which says something, well, so don't worry too much about this. If you think back to this graph G, you remember that we didn't just have the associated link LG, we also had a surface FG. That was sort of a thickening of this graph. So now if you place this whole thing in S3, so just compactify R3 with 1 point, place this whole thing in S3, look at the complement of FG, the surface, and then kind of notice that on the boundary of this complement, there lives LG, the knot. Then you get yourself a so-called sutured manifold. It's just what I just said is a kind of representative example of a sutured manifold. Those things have a Floer homology group associated to them. Okay, can't explain what that means, sorry, unless after the talk. Well, fluid homology always falls apart into a direct sum. Direct summands being well labeled by so-called spin-C structures. This one obviously comes from some physics. Anyhow, the theorem states that these spin-C structures for this particular construction are affine equivalent to a set of hypertrees. So even though the big root polytope was just a combinatorial gadget, these hypertrees are not just a combinatorial gadget, they do occur in topology. Well, through some advanced stuff. This is not easy stuff. But a corollary of that is that some Humphrey coefficients can actually be computed from fluid homology. Because that's what this is doing. You take the right fluid homology so that the set of spin-C structures ends up the hypertrees that you want. And then you do that other business that I didn't explain about the activities and the distribution of the statistic. And you end up with H star, which is the top of the Humphrey polynomial. All right, so this probably does not impress anybody that's not in mathematics. However, in mathematics, this was very nice. Because these two things, the Humphrey polynomial and fluid homology, have very different natures. And people are looking for a common framework into which both of these theories would fit. And what I explained today is a manifestation that such a framework should exist. It's not a complete answer to the question, of course, because you notice that I was talking about fairly special knots. I was talking about only certain coefficients for those fairly special knots. Definitely, I didn't get to the bottom of this. Well, but hopefully at some point I will. So I'm still working on that, more coefficients and for more general knots. Maybe I even want to categorify the Humphrey polynomial, never mind that. I also want to develop more of this combinatorial theory to help me answer these questions 1 and 2. And most importantly for us right now, today, I do want to see if these ideas have any relevance, any applications to what we are doing here, such as line defects in liquid crystals or any other physical systems. Okay, I'm still a minute early, but this is the end of the talk. Thank you.